Good morning, everybody. This is Elliot Wickham with NOAA's NIDIS. Welcome to the Southeast Monthly Climate Webinar for April. Today, we will be going over the climate overview. I will be giving that instead of Chris Furman from the Southeast Regional Climate Center. He's just not available today, so I'll be covering for him. Next, we'll have Shelby Saxon covering the water resources overview, Pam Knox covering the agricultural impact update, and then our special topic today will be coastal flooding in the Southeast by John Callahan and Anna Keeney from NOAA's Center for Operational Oceanographic Products and Services. If you have any questions, feel free to type your comments in or questions in the question box at any time, and we'll answer them when we get to the end with our Q&A. All right, so for climate discussion today, over the past month, temperatures have generally been near normal around the southern part of Florida into parts of Alabama and Georgia, and then moving northward, temperatures have generally been above normal, ranging from 3 to even 5 or 6 degrees above normal, getting into portions of North Carolina and Virginia. For the Puerto Rico and U.S. Virgin Islands, temperatures have been closer to normal, ranging 0 to 2 degrees above normal. For precipitation over the last month, it's been either hit or miss across the region, although generally most of the region has seen below normal precipitation, which you can see by those the brown coloration there. And then portions of Alabama and Georgia, they've been more of the wetter parts of the region. And then in Puerto Rico and the Virgin Islands, precipitation has generally been above normal. So for the U.S. Drought Monitor, we've seen some changes, both good and bad, over the last month. In general, we've seen a decrease in conditions across the region, mostly across Alabama, Tennessee, and Georgia, but some changes in North Carolina and South Carolina as well. One good note is Alabama. This is the first time since last April 2024 that they've actually been color-free or free from any conditions on the U.S. Drought Monitor map. Unfortunately, though, over the last month, both Virginia and Florida have seen an increase in conditions, primarily in Florida with an expansion of D2 or severe drought conditions, and the addition of extreme drought there in South Florida, D3. All right, for ENSO El Nino, on April 10th, they issued a final La Nina advisory, and this is issued after La Nina conditions have ended. And now moving forward, we are in ENSO neutral conditions, which are favored for the Northern Hemisphere for summer, with a greater than 50% chance of this condition continuing through the August-October timeframe. Looking forward, for the next 6 to 10 days, temperatures are going to be above normal, while precipitation is generally going to be near or below normal for the region, except for the southern tip of Florida and western Tennessee. There might see some above normal conditions for precip. 8 to 14 day temperatures, again, staying above normal. That's the pattern as we see, just above normal temperatures. And then we see some more above normal precipitations coming into Alabama and portions of Georgia and Florida, but near normal conditions will be prevalent for North Carolina, South Carolina, portions of Georgia and Virginia as well. Then 3 to 4 weeks, mix of conditions for precipitation, generally for the southern portions of the region, below normal. Precipitation is forecast, and then changing to above normal as we move into portions of Tennessee and Virginia, with equal chances across the northern portions of Alabama, Georgia, and South Carolina, as well as North Carolina. And temperatures are expected to be above normal through the region as well for the next 3 to 4 weeks. And then the seasonal drought outlook. I know that this looks out more than our towards our next webinar in May, but that the monthly drought outlook will be released in a few days. So we don't have that product yet. So looking at what the seasonal the 3 month looks like, they're showing improvement in drought conditions for most of the region, and then some of those drought conditions will improve, but still linger in Florida and in portions of Virginia and a little bit of North Carolina as well. Here is the summary, which you can go back and read at your leisure, but I'll go ahead and pass it off to Shelby for our water resources update.
Thank you, Elliot. And we can go ahead to my first slide. So we're going to start looking at the 28-day average stream flows. The entire Southeast is around normal. Rain in the beginning of April was able to take us from below normal to normal. But since then, we haven't seen much, and it looks like we're headed to the decline again. As Elliot said, most of that rain was in Alabama and Georgia. And so most of that increase that we see in our 28-day average runoff graphic is from having above normal and normal flows in Alabama and Georgia. And so we can go to the next slide to get a state by state look at runoff. And so starting in Alabama, where rain amounts in the beginning of April were somewhere between 3 inches and 20 inches, depending on where you were. Down in the southern near Mobile Bay, we had greater rainfall accumulations and more widespread within like the 3 to 8 inch range across the state. And so we observed the runoff quickly springing from below normal to normal there. And as of, I think this past weekend, we just started working most of that flood wave out into the Gulf system. And so runoff there is still holding at normal. And then similar in Georgia, where most of the rain there kind of stayed towards the border of Georgia and Alabama and in northern Georgia. So it wasn't quite as widespread as it was in Alabama. And so we didn't see kind of like a dramatic runoff increase just because it wasn't statewide. But we did have somewhat of a rebound where we looked like if that event had not occurred, we would have been trending on that below normal line that we were at in our last webinar series. So thankful for that rain that we did receive to hold our runoff levels there. In Florida, we haven't quite reached the wet season. That won't kick off until around August, but the streams are really starting to dry out there. And so runoff is falling into that below normal area, and we're back near where we were in the beginning of the year, back in kind of January timeframe. So streams are really falling off. We can go to the next slide where we'll get looking at the Carolinas and Virginia. And so in the Carolinas, things have been pretty dry. Our frontal systems have kind of continued to move in this east-northeast trajectory. And so a lot of that heavy rainfall is just missing the Carolinas. And so we're seeing South Carolina and below normal and falling and runoff, as well as in North Carolina. Virginia, I believe outside of our area is where most of its spring from the much below normal to normal happened. And that was the same system, but because the western areas of Virginia did have higher accumulations, we did have some rebound into the below normal and nearly normal areas for there. And so on our next slide, we'll look at our current flooding conditions. And so, though the rainfall deficits have been a big story for the past month, we did have some floods occur in Alabama near Mobile Bay. Where those greatest accumulations were, we actually had a major flood on the Styx River, and so that was a significant event down there. There was also some moderate floods, but mostly throughout Georgia and Alabama, we only saw bank full conditions and minor flooding. And so, as we have currently, the bank full conditions that were on the Altamaha River and the minor floods that we saw there are still kind of making their way to the Atlantic coast. And so we have a few bankful conditions still going. And we can go to the next slide and we'll talk about where we are in terms of river flooding. And so this is week 17, and we are past our typical recharge season for Alabama, Georgia, the Carolinas, and Virginia now. And so the number of river floods that we expect are decreasing now, and that is due to changes in the weather pattern as we shift into the spring, competition for water resources, and temperature increases that we'll see going forward. And in our next slide, we'll kind of go into Florida specifically because their wet season is different from the other states, and it hasn't quite kicked off yet. And so we're still in a low period for river floods there. But as the weeks continue, we're hopeful that the rain season will kick in and our stream flows will start to rebound. And so, uh, looking forward to the next few months, we're at normal risk for river flooding across most of the states. Um, we do have that above normal rainfall that is expected, but with the dry conditions that we've been seeing, we are remaining at normal risk. Only area that we've highlighted as having a slightly above normal risk would be in that South Alabama area where those great rainfall accumulations have been. And really, our March heavy rain event was also down in this area. And so that has just led to this area being above normal. In climatology for stream flows, and so we're highlighting this area as a possibility to be slightly above normal river flooding. And so I believe my next slide is just the summary that you all can read at your pleasure. And if you have any questions, my email is at the end here. And I'll hand it off to Pam to talk about agriculture.
All right, well, thank you very much, Shelby, and good morning, everybody. It is a great day here in Athens. We have not had any rain since April 11, and I'm excited because we might see some today. It probably won't be a lot, but every little bit helps. And so I also want to just say that I'm happy to say that the regional climate centers have just been funded. It's going to make my job a lot easier, and I appreciate all the comments I've seen about that. We're really happy to have them back. So let's jump right into the impacts of recent conditions on agriculture. Looking at the statistics from the National Ag Statistics Service, we can see that more than half of the corn has already been planted in Georgia and South Carolina. About a third is done in Alabama, and that statistic now is almost a week old, so I'm guessing that they've really accelerated planting that, and they're starting to move on to other commodity crops. All the fruit is looking really good. The blueberries, strawberries, and peaches all look like they're going to have a bumper crop this year because we didn't have a late frost. In fact, the peaches are being thinned so that they can improve their size for the market. Some years the frost kind of does the thinning for them, but this year they're having to do it either mechanically or chemically. And so it's good. It looks like it's going to be a really good season for fruit producers this year. The Vidalia onion harvest has begun in Georgia. It's always a big deal for us here. There's just a few counties that are allowed to produce these particular sweet onions, and the pack date this year was April 15, so they are starting to appear in the markets now, and I'm looking forward to that. Winter greens look like they're developing well. They're just a little bit behind last year, but in general they're doing pretty well, and some of the oats and wheat are starting to head out a little bit as well. Cotton and peanuts are now starting to be planted. It's going to be increasing a lot in the next week, especially if we get a little bit of rain, although really most of the rain in Georgia at least is probably going to be in the northern part of the state and not too much in the south. But we'll hope that we'll get some more rain coming up soon so that there's some moisture in the soil. Melons and summer vegetables are now being planted as well. They're starting to see some insect pressure and some disease pressure from fungal diseases where it's been moist enough, so that's something that they really will need to stay on top of. And because there has not been a lot of rainfall, farmers do need to keep up on irrigation. Makes it a little tough for dryland farmers, of course, but we will be hopeful that we'll get more rain soon. So let's jump on to the next slide. Here's just some examples of the soil temperature on the left and soil moisture on the right. Again, keep in mind that these were from late last week, so things probably have changed. For example, the soil temperature on the left is showing a lot of the southern part of the region as cooler than normal temperatures, but with all the warm temperatures we've had over the last few days, it would really surprise me if that doesn't change soon. Not much rain, so most of the sunlight's going right into the ground and heating things up. You can see in the northern part of the region, we do have warmer than usual temperatures. And then if we look at soil moisture on the right map, there is quite a bit of soil moisture in eastern Virginia, but nearly everywhere else in the region is drier than usual. And this is the top 100 centimeters, so it's a pretty deep profile. You can see some of the deep soil moisture. It's not really showing up on the drought monitor because there has been some rain that's hit the surface parts, but it hasn't gotten very far down into the soil yet. So in the root zone and lower parts of the profile, it has been a little bit dry. We go on. Spring bloom, you can see this is from the National Phenology Network. We've been showing this every month. And you can see the spring first bloom is now above our region. And so this will be the last time you'll see this until next spring. But it just shows how much earlier than usual a lot of the bloom was this year. In some cases up to about 20 days, well, not 20, but maybe 15 days earlier than usual in a lot of the region, except for Florida. And so we were really lucky we did not have the frost. Speaking of frost, here's the map for the last frost days. We're already past the average date of the last frost for the whole region, but there is a 1 in 10% climatological chance of a late frost in the North Carolina and Georgia mountains still after today. However, I did look ahead at the long-range models, and it doesn't look like we have any cold outbreaks coming. So I think we're pretty much done with the frost for this spring, and I won't be showing this map again until next year. So if we go on, soil temperatures are what are used commonly to decide when to plant, along with soil moisture. The map on the left is from the University of Georgia Weather Network, and it shows this is the 4-inch soil temperatures from from Sunday afternoon, and it shows that temperatures are relatively warm across really the entire state, but especially the southern half, which is more sandy and certainly where more of the commodity crops are planted. So from a soil temperature perspective, things are pretty much wide open. People can plant as they need to. North Carolina map on the right-hand side there shows certainly the eastern 2/3 of North Carolina is also above 70, except for that one value of 59, some local thing there. And the mountains, of course, are a little bit cooler because they're higher in elevation and they've had more rain. But that also is an area where a lot of stuff is being planted right now. So if we go on, growing degree days for the year. This is base 50. You can go to agroclimate.org and put in your own base if you want. They have a few different choices. And this is the deviation on the left-hand side here for the last 30 days. You can see a lot of the region, that green and even blue in some areas is lower than normal growing degree day accumulation, except for the South Florida area. And if you look at the map or the graph on the right-hand side, this is for Tifton in southwest Georgia. You can see there was a long period from early April to mid-April where it kind of flattens out, which means that it's not accumulating very fast. That has accelerated in the last few days, and so I would expect that that is going to continue to be a little bit above normal and follow the higher end of that red envelope. You can see we're a little bit ahead of last season and also the historic average. And so, good news for the farmers who are looking to see their plants develop quickly. We'd like to get the harvest in before we have too much problem with the tropical season, but we'll see. We go on. There's my summary of what's going on. You can read that later. And now it's my pleasure to introduce our special guests today, Anna Keeney and John Callahan, who are going to be talking about coastal flooding. And I will let them do their own introductions so that they can maximize the time.
Hey, thanks, Pam. Can you hear me? Can everyone hear me out there?
Yep, we can hear you.
Okay, wonderful. I'll just say hi for myself, and then I'll pass it off for John for a moment before we kick things off. Thanks for having me today. It's actually been really fun to listen into another side of science for this morning. Since I deal mostly with flooding, I don't get to hear about droughts very often, but I am a coastal hazards oceanographer with NOAA's Center for Operational Oceanographics and Products and Services. And my colleague and I, Dr. John Callahan here, will be talking to you a little bit today about the coastal reanalysis and the ways that we're using it to evolve our observation-based mapping and inundation program. So John, did you want to introduce yourself as well before I kick things off?
Sure, quickly. I also just want to say hi to everyone. And I also work with Anna in the National Ocean Service with co-ops using or looking at coastal flooding in particular from all timescales. Myself, I'm actually a climate scientist and not an oceanographer. So it's been very interesting to work at a group focusing on kind of a more holistic approach to coastal hazards. And I know we've seen a lot of things here in the presentation in terms of hydrometeorology, agriculture, et cetera. We're going to talk about the coastal side here. So it's been very interesting to integrate all these things together. So,
Yeah,
more later.
absolutely. Thanks, John. So today we plan to have a rich presentation for you, and I think we have plenty of time to cover the topics in our deck, as well as time for questions. So we'll explain a little bit more about the coastal ocean reanalysis we lovingly refer to as CORA. We'll talk about the stakeholder engagement framework that made it all possible and supported the community modeling effort that made CORA, the ways that we're applying it to subseasonal to annual forecasting, and most importantly, while we still have it available, data accessibility and ongoing research and development. So with that, let me just click over to the next slide. And again, just before I go into the ways that we're using our stations to increase the resolution through modeling, I like to remind people that all of this information comes from the Sentinels of the Coast, which are our National Water Level Observation Network. Our navigation support is our bread and butter, but we have this amazing coastal hazards program that helps to create some derived products. But mostly in general, it's all about keeping everybody safe and healthy at the coast and supporting our blue economy. And it's done, and the observations that are collected from these NLON stations across the country have led to the ability to reduce bridge elisions and collisions, support the multi-sensor time series efforts of the NOAA Ports program, and really just protects our coastal communities because 40% of the U.S. lives within 100 miles of the coasts. And we have several products at different time scales that help people understand and plan for and mitigate the impacts of coastal flooding. And I just am super thankful that I live in an office, or I work, I feel like I live here now. I work for and in an office that's dedicated to innovation. And so hopefully we can show you a little bit more about how we've been able to do that today. So what is CORA? It's the Coastal Ocean Reanalysis. And as I mentioned before, that leverages the observations, the multi-decadal, sometimes over 150 years, which is before the Civil War. That kind of blew my mind. So these stations across the country collect the data, and CORA helps to bridge the gaps in this data. We've used modern modeling to prototype what it looks like to make projections off of this. We'll talk a little bit more about that in the future. But all of this is done so that we can enhance the footprint of our historical water level data, so that it's not just, at those tide stations 10 to 20 miles apart. It's a nationwide data set. So we made the investment early on, and it's because more than just meeting the needs of some of our coastal communities, it's also meeting the collective needs that we put together as the National Ocean Service, based on how we kind of want to provide for resilient, climate ready coastal communities, and it supports the goals that are outlined in the climate timescales paper that I'll be able to go over in a little bit more detail in the next slide. But Cora essentially gives us the backbone to be able to create long-term water level information and building baseline climatologies. Like, that's one of the privileges that John and I have of working with each other. We're multidisciplinary, speaking the same language, but ultimately using the work that we're doing to benefit not just coastal flooding, but also really understanding climate timescales and being able to help collaboratively plan for the future. And as I mentioned, we did this in a really thoughtful way. It took years of listening to the people that we engage with. And so we took the input from our different regional offices with the Office of Coast Management, our other observation networks through the Integrated Ocean Observing System called IUS. And we listened to what the needs were. And then we came back to the table through this loop here. We figured out what data sources would be useful, what research would be possible with these data sources to meet the needs of these communities. And we went back to them and we said, hey, does this product development look like what you would actually need? So we keep working the stages of this wheel here so that we can build and gather and translate and assess and address and deliver all these things that are important when you build products and services for people, not just the sake of science. And we keep that door open for continued communication here as well. Also outlined in that CICT paper here is just kind of where we've come from as far as climate scales or climate time scales. We have a good resolution of the past right now. We've been able to do lots of analysis with the records we currently keep. We improve our observations and monitoring systems so that we can have better watches and warnings. We have a lot of skill in our short and medium range forecasts, but this is where the sweet spot that we're working on right now is better understanding through this work the subseasonal and seasonal outlooks, and then ultimately making climate projections from them, because this data covers roughly 44 years from 1979 to 2022. So where do we bridge the gap here? How do we fill in the spaces in between? Reanalysis is something that's been common in the Weather Service and is common throughout science. Even the approach that they're doing here, which is called a coupled approach, is useful, but it's never been done with ocean data, and that's what makes Cora so unique. So we've coupled AdCirc, which is an advanced circulation model that helps us model historical water levels. It's here on the top. And we've combined that with SWAN, which helps us understand the short nearshore wave system. So between those two, we have a pretty collective idea of the way that water levels are moving through atmospheric pressure applied by ERA5. That's the European reanalysis. And it's the most advanced reanalysis of different atmospheric components. And so using those three combinations of AdCirc and SWAN for modeling, and then ERA5 for the climate drivers, helps us create, it creates really valuable high resolution information. Basically, that mesh that you saw previously, all these little crisscross triangles are actually a series of centroids that are all connected together. And that is the resolution of the data set that we're providing. It's pretty amazing. It's roughly every 500 meters. And then again, what makes Cora unique is that we do this in multiple steps. We run the initial models. We see what we develop as far as high resolution, and then we go a step further through assimilating the observations that we've collected. So the first set of models I ran, or we described, are called the priors, and then we take all this really valuable information, and while this slide is not necessarily showing you historical water levels, it's showing you just how much the sea level trends have changed over time. And with Cora, we're actually able to model that same term water level change. So you can see sea level rise, you can see interannual variability. But that step of integrating all of our observations basically creates an error field where you can correct and level up the model so it better meets your observations. And that, once we reach that point, that's kind of the assimilation point, we run it all again. So the three-part process of this, it gives us the best high resolution, accurate data set, or data that we can provide to people. Our own tides and currents are set to a parameter of within 10 centimeters for our predictions, and Cora is also meeting that in most locations, except for where we haven't been able to complete the station record. So long story short, this is a really awesome, impactful slide that shows you where the star is Charleston, but where everywhere else that you see those green dots or the grid over top of it that I'll tell you more about in a moment is where we're able to produce this historical data at a much higher resolution, and where we can begin to actually layer other pieces of information on top of that, like maximum water levels. So this is an example here, I think, from the Wilmington area. This is the inland Wilmington, and then this is the Wrightsville Beach station over here on the right. And just the color range here in the symbology shows where you've experienced more flooding through this 44-year time period, and where you haven't. And while this map isn't yet interactive, I'll link you to the ones that are interactive later on in the presentation. And you can click on each one of these centroids and actually see what the maximum water level was and when, so that we have an immensely rich two-dimensional water level product that has been validated by our partners at the University of Hawaii Sea Level Center. Much like co-ops, they are involved in putting instrumentation in place to be able to better understand the specific geomorphology and ocean impacts in that area. And then we take that data they take that data and they make products and services from them. So they were extremely interested in our work with Cora, and Dr. Linta Rose here did an amazing case study about Hurricane Irma in 2017, where she was actually able to determine through flood frequency analysis which of these centroids remained wet throughout the entire hurricane process of Hurricane Irma, which ones on land stayed dry, which ones were intertidal, and those that flooded during the extremes that we expect to be around this area with red, which denotes the low-lying areas along that coastline. So all that to say, it's been wonderful to work with them. They were able to prove that Cora is exceptional compared to some of the other global models like Loris. There's a lot to kind of see on this one, but if we just focus on the gray observations and then the blue in Cora, you can see that Cora is closely mimicking what we have seen in observations, with the known caveat that we'll talk about a little bit later about tropical cyclone influence. But overall, I heard some feedback. Is everything okay still? Okay, I'm just going to keep on going, I think. That was the preliminary version of Cora 0.9, and then we released in January version 1.1, which has a much more complete station record. We were able to use our sea level trends and subset from those monthly values into hourly values so that we can make a really powerful or more complete record of historical data in the Gulf and ultimately improve our accuracy of our modeling again. So version 1.1 is the newest and greatest that we have out and available through NOAA's Open Data Dissemination Platform. And I think this is where, am I handing this over to you now, John?
Yes, you are.
All right, go ahead.
All right, thanks. Hey, so the model itself, Anna mentioned that it's a kind of a couple model between AdCirc and SWAN, right? AdCirc for the water levels, SWAN for the waves, and there is a wave component to the water level that comes out of the Cora reanalysis product. And what it's forced by, Anna also mentioned about kind of our first runs or prior, and the second runs we call it, posterior or the output. So there is a two-phase approach to how this is run. The initial forcing in our prior runs, it's forced by ERA 5 meteorology. In particular, we're talking about surface winds and atmospheric pressure. And also the tides. And this is run by the TPXO tidal model. It's a global tidal model. I think it's about 9 or 10 different tidal forcing constituents, from high frequency to the fortnightly and actually monthly. And it also has some nodal corrections if you're familiar with kind of the way the tides work. So it's a pretty well-used astronomical tide forcing global model, which was pretty good. So these are the two forcing functions, next slide, that we use to run to develop our priors. This is focused on the coast, as we've mentioned, and there are not too many reanalysis products that are out there that actually are not either land-based or ocean-based. This is coast. So it's forced with the observations from the tide gauge. And the way that the forcing, or the data, I'll say the data assimilation is done, is that, again, as I mentioned, it's kind of a two-phase approach. We run it once based on the forcing, as I mentioned, the ERA 5 meteorology and the tides. Then once we do that, we look at the errors between that prior run and the observations from the tide gauges. And we do that in two different timescales: monthly mean sea levels from these tide gauges to, of course, the Cora prior run. But also we look at a 36-hour low pass filter of the residuals. So the difference between the tides itself and the observed water level, you take that, you filter around 36 hours so we don't get some of the high resolution, like the high frequency tidal noise, but it gives us a good feel on the daily variation. And what we do is we take those for both of those two timescales and develop these correction fields and interpolate those correction fields down to hourly time steps that the model is actually run on. So we take a look at that, and we actually have 53 stations that you can see here in the green. These are the ones that we actually developed the correction surfaces for that are part of the data assimilation. Excuse me, those are not the green, the actual gold diamonds. And then we have a remaining 59 stations that we use for validation and testing of the model. Next slide. So I mentioned those two different forcing factors, or two different, looking at error terms, and we look at these again as correction surfaces. So really what we could look at is we have the monthly and the hourly, again, interpolated down to an actually hourly time step, and we develop this overall correction surface that we call more of a dynamic water level correction surface. And this is actually forced into the model. And it's not forced into the model as you would typically think of a data assimilation scheme of just kind of a subtraction at these different locations. It's actually done by going back into the model forcing terms. And actually, it's the atmospheric pressure forcing term that the force, kind of like pseudo forces, are enough to change the correction of the water levels produced. And in this way, it actually has mass continuity and force continuity throughout the model propagation run. So it actually, I think it's a very interesting way to do a data assimilation scheme. Next. So basically summarizing what I just mentioned, this is the slide I wanted to be on. It's really combining, now we have this additional force term inside the model forcing components. So this is what actually is the posterior run of what comes out is the combination of these three. And it does take a while to run because we have to run it once with just the meteorology and the tides, then look at the error terms, then run the whole thing again with the dynamic water level correction surface. So we do this 1 year at a time. So it's able to, we can run multiple years simultaneously. When we go through, we do 44 years, we can run multiple years, again, simultaneously in depending on computing power. Okay, next slide. Well, when we do the testing or the validation of the models, you can see both the red and the blue PDFs there. And the red is kind of that prior run. If we took a look at the error surfaces and against the tide gauges, and you could see the RMSE errors in the table on the left, and again, the distributions on the right. RMSE's errors are, in this case, 18 to 20 centimeters. Average MAE errors, 15 or so centimeters, which is not too bad. And it depends on what location you are. Some locations do much better than others. But once we add in the correction services, as anticipated and expected, of course, the RMSEs and the MAEs drop significantly, but also the error, not only is it bias corrected, essentially, but also the error and the deviation of the errors is significantly narrowed. So we have much more confidence, of course, in the water level predictions and forecasts that Cora makes. And of course, looking at the assimilation versus, or the, looking at the assimilated stations versus the validation stations, we do see improved performance at those assimilation stations. Again, of course, that's kind of expected. Those stations that are assimilated into the procedure have a better accuracy. Not significantly better, but better accuracy, yes. Okay, next slide. We took a little bit more looking at the skill assessment, not just the overall RMSE and MAE of the forecast from Cora predictions, but we looked at some specific ones. And I'll show you here calculation of datums and also how well it matches the extremes or the daily maximum water levels. We did this at 43 stations, ones that have a more accurate continuous data record. Next slide. So looking at the datums themselves, and again, this is kind of that mean higher high water datum on the top panel, the mean lower low water datum on the bottom panel. And this is kind of like the average of the higher of the high tides or the lower of the low tides. And you can see this graph, it kind of goes from the far left is in the Gulf, going kind of northward through Florida, the southeast, and then kind of ending up in Maine in the far northeast. And you can see accuracy is pretty good looking at those mean higher and mean low water. Just a few centimeters difference. Again, about 3 or 4 centimeters difference on these datums. And this is extremely important as a reference, as many products that use tides, whether it's flooding, agricultural planning, etc., wetland planning, specifically building of infrastructure and roads, All right, that mean high water in particular is extremely important. Next slide. Oh, and there are some specific ones that kind of stand out. Oh, sorry about that. You can go back on one. Forgot I had this animation in there. There were a couple of them that do stand out as a little bit different than the others, where Cora here, in the red actually underestimates the high, underestimates the low as well. These are ones that are upriver, up, I believe, Cape Fear River in Wilmington, North Carolina. Actually, the picture that Anna showed a few slides ago, but also up the Delaware River as well. So these are areas that, again, are maybe precipitation or stream flow influenced that this model does not take into account. So these are particular areas that we're looking into to improve the process in the future. Okay, now next slide. And the last thing I want to show is not just the datums, but let's look at the extremes. In this particular case, this is the 10-year return interval, and this is of the water levels at the coast at these tide gauges. And again, looking at the unassimilated, kind of the prior runs versus the assimilated, the posterior runs, the red versus the blue, again, it significantly increases the accuracy by using that data assimilation scheme. And the overall errors majority is about within 10 to 15 centimeters, which looking at that 1 in 10-year level, that 10-year return level, I think is pretty good. It gives us, again, some decent confidence in how we could use Cora, looking at these 43 years of observations in the past to give us a better feel, right, for what is historical terms, again, between the tide gauges, right? We have a lot of data at the tide gauges, but what about in between? We're feeling more confident, at least having a good sense of what's going on between those gauges. Next slide. And Anna, I think I pass it back to you.
You got it. Yeah, so thank you, John, for outlining some of the details that kind of go into all the aspects of Cora's modeling and the ways that we've corrected it. And that's because we've had these applications and these use cases in mind. So might be familiar to some of the people. I heard, Elliot, that you work there at the University of Alabama. So we're actually working with partners at University of Alabama and also University of South Florida to take a subset of those centroids that dot the coast and to turn those into, you can't see me air quoting, but virtual stations. Essentially, if you have a historic value or water level over there, you can use that to make predictions from it. So again, working with our academic partners to be able to better understand flood frequency analysis for more regional understanding. And because it's so impactful, like you've seen in the other slides, to be able to just see with your eyes and then get the data to support it, which doesn't happen in all of our products right now, but is extremely powerful for flood risk planning, like John was saying, prioritizing areas of green, of marsh restoration or green infrastructure, so that people can have a more nuanced and collected understanding of exactly what kind of floods impact areas. Like this example in New Orleans, where you can clearly see the influence of the Mississippi River contributing to flooding, whereas on the other sides of the Gulf, not so much, even through that 44-year period. And when you think about 44 years of data every 500 meters of the coast, it's many, many terabytes. By the time this national model is complete, we'll be well over 100. We have over 20 now. So it's the richness and the nuance of all this data is really helpful for machine learning and AI applications. And, the more educated a model can be, the better predictions that come out of it. So those are some of the collaborative efforts, but even internally, and I forgot to mention this earlier, but through the time series of information, we also host a product called the Coastal Inundation Dashboard. It's a really powerful near and real-time tool that lets you know which stations are expected to flood within a 48-hour period. That's what you see, these little pings on the dots or on the pins over the stations. But what you also see here is a layer from the National Weather Service that basically tells people these are coastal hazard polygons. This one happens to be storm surge, and using Cora to kind of Cora can be helpful for painting a better picture about where these flooding impacts are actually happening most. Instead of highlighting an entire county, you could only highlight the areas that we know are susceptible and low-lying to flood, or we know are low-lying and susceptible to flooding. So this example here in the middle, the area in red are all the minor high tide flooding zones where we expect to see routine minor high tide flooding. And then this is another product, the monthly high tide flooding outlook, allows you to, it uses a probabilistic model to predict how many, or predict the likelihood of high tide flooding by day up to a year in advance. And so if you were to hover over to one of these dots in the product, you would see the flood likelihood. So these light pins are between, I think, 25 and 50%. Over 50% you would see in red. But so the idea is that Cora can refine polygons, help you get a more nuanced picture of exactly what type of flooding is expected or predicted in an area, and then also use it to enhance our digital elevation models, DEMs, and our other mapping increments like the half-foot increments that our partners at Office of Coast Management are working for. So we're hoping that the next generation of the sea level calculator has Cora gridded dot values as a basis for this, for the work that we're doing too. And John, was I going to hand it to you? Yes, for these ones as well.
Yes. Yes, this is one example of an application that we are actively researching on how best to use Cora in this current product. You may be familiar with this. This is the monthly high tide flooding outlook. And as Anna mentioned, she alluded to, it's looking at the probability or the likelihood of flooding, in this particular case, of water levels reaching or exceeding, a defined threshold, NWS or NOS defined threshold along the coast, at each day out to 12 months lead time. And really the model, if you're familiar with the model, or if not, you can see it here, right? The water levels observed are really a combination of the tides plus this long-term trend that's been going on. We look at those relative to whatever that impact flood threshold is, take a look at that difference at each hour and each day, and develop these probability distributions. We do it by month because there is a seasonal impact of those. And then look at this data persistence, right? If we're already a little bit above or below average, right, those water levels definitely persist at least for a month and likely 3 or 4 months in some locations, but definitely a month. So we have a persistence model built in. So it's data-driven model. This is out there right now. Next slide. But one of the problems, one more. So here we go, is that we look at it, right? We have this great model. It's built at the tide gauges. You can click on a tide gauge. You see the calendar as you see here on the right. And again, this is operational right now. And it gives you a likelihood, again, of each day through this calendar view out to the future on, is it unlikely for flooding to happen based on climatological data and data persistence versus, potential flooding and then likely flooding. So we have it 3 categories. And this is, again, it's only at the tide gauges, but it's a good model driven a lot by the tides and seasonality. Next slide. And from talking with users and stakeholders, the idea was that, well, this is a great model and it's an outlook of flooding, anywhere from the minor flooding to the major flooding, combination of all of those. But, we want the information in between the gauges. Some of those gauges are tens of miles, sometimes longer in between those gauges. In between that, and that's one of the use cases of Cora. Next slide. So we can take this, the information we have Cora, the model itself, thinking about all of the nodes that we see, spaced, roughly up to 500 meters, 2 to 500 meters, interpolate it down to like a 500-meter grid. Next slide. And then the same kinds of things that we do at those tide gauges, we can actually look at like these virtual gauges all along the coast. We have the same data, 43 years of hourly data. Next slide. And then we can kind of look at those by clicking on each of those areas. Think of those again as virtual tide gauges, and we can get the same kind of information because the tides, the trends, the data persistence model, et cetera, those are all can be computed from the Cora observations. Next slide. So that's kind of the idea that maybe the future of this product could go from points to locations and places with that spatial variation. So that's what we're actively moving right now, is it including Cora into our high tide flooding outlooks. Anna, pass back to you.
Thanks, John. And we'll be wrapping it up here shortly. So as I don't know if we actually mentioned it, but at the moment, Cora is expansive of the Gulf, the East Coast, and the Caribbean. So we call it the GEC. But we're actively modeling the Pacific coast of the US, Hawaii, and the southern parts of Alaska at the moment. Those are what we're running those prior runs right now with our partners at the University of North Carolina. With plans to also include a tropical cyclone field in the future. So we're not sure if this current model will have that, but we are also creating the patches that kind of work to build in tropical cyclone influences impacts in Cora modeling as well. So I won't go over every single detail, but we have a lot of plans that are still in the works. And as long as we can keep doing them, we are going to keep doing them. We have lots of thoughts about how we can improve the accuracy to even below that 15 centimeter mark, as John said, but we are keeping on, because it really kind of shows the impact of what can be done through these models. It underpins data and makes it possible to provide that in areas that haven't been before. And to expand on the accuracy of it. So like this is an example here, Dr. Ludick at UNC is just showing kind of the impacts just from a high level here of what the wind speeds look like through ERA5. But if you actually include the tropical cyclone winds through that patching process that he's working on documenting, you have a much more clear understanding and impact of what is expected historically, or what's been, in between. At the moment, this, like I've mentioned before, is all available in the nod, but we have a lovely tides and currents landing page here. This is a little bit of an outdated slide, I apologize. But everything is in one place. If you scan that QR code with your phone, or if you go to tidesandcurrents.noaa.gov/Cora, you can find this website that helps you understand exactly what Cora is. This is also where there will be links to the maps that I talked about that are interactive. So if you click on one of these, it'll take you to a new pop-up where you can explore all the data here with the maximum water levels, along with our water level stations in blue. And we didn't discuss in full the reason why we've had gridded data as well as centroids, but this grid is what allows us to have the infrastructure for continuous geospatial resolution, but also to be able to add multiple climate variables to this. So you're not just talking about water levels, you're talking about barometric pressure, you have grids of winds on top of it. You have all this gridded data that kind of works together. And it's important because the grid is universal and evergreen now, but the data underneath often changes. Like I said, when we add tropical cyclones, that'll be a different version, but the grid production will allow us to be able to map and visualize a ton of climate variables in a way that it plans for the future. So this grid is also, it's built around expecting water levels up to 10 meters more than what are currently viewed in the historical data. But both of those maps are interactive on the website. You'll have a ton of use cases and every frequently asked question that we've come up with so far, but I welcome your feedback, your ideas, your thoughts. All of that's important. And most importantly, accessing the data. It's if you go to the resources tab on that website, it's this analyze and access and analyze link on GitHub that we're working on featuring a little bit more prominently on the page soon. We have a user guide in the works as well. But this notebook is a GitHub notebook that stores a Python code that allows you to benefit from the cloud-based optimization that we've put into place to access this massive data set. You can kind of subset it through these data, through these notebooks. You can pick a location through latitude and longitude. You can pick a subset of time, like maybe for a certain year or a certain event, like we've seen in other use cases here. But links to that are all available on the website. That is, and the data, like I said, is hosted in our NOAA open data dissemination platform that is heavily and solely reliant on our Amazon Web Services contracts right now. So fingers crossed that those are maintained so that we can keep providing this really valuable data sets to people, or that we can keep providing them to people. And caveat that if you're interested, please download now, because you never know how long we have anymore, unfortunately. But yeah, like I said, this has been a community-based modeling effort through so many academic partners, so many internal partners. I've mentioned several of them throughout this presentation. I think I haven't talked fully about our partners at RPS Group or Tetra Tech. They are the ones that helped us chunk and kerchunk all of this data into something that's usable. And I just wanted to say thank you for the opportunity to run through all of this in such detail. Great to hear your voices, and hopefully we get to return to conversations in the future. We welcome any questions. Thank you.
Anna and John, thank you so much for that wonderful information, as well as Pam and Shelby. Thank you so much for providing your updates as well. I want to invite all our participants to please, if you have any questions, you're more than welcome to put them in the question box and we can go through a little bit of a Q&A if you have any questions. But once again, thank you all to everyone that provided thank you everyone for your presentations today. They were very, very informative, and I myself learned a lot about that. So thank you. just going to go ahead and watch the chat box here. So far, no necessary questions, but just some thank yous of for the great work that's being done, and sharing the the thanks for the use of these products. And yes, just so everyone's aware, there will be a recording that comes out from this presentation. So probably later today or tomorrow, anyone that was part of this presentation, it will be recorded, and that link for the recording will be sent out to you all. Hey, Anna and John, I do have a question for you here. Question is, are future assessments planned of tidal gauges that have freshwater influence?
I guess assessments. I would like to know more about what you mean by assessment, but I do think that we're actively coupling with the Water Center and working with USGS to incorporate their stream gauge information and their modeling that happens at the same resolution as Cora, so that we have a little bit more of a holistic understanding of water at the coast. So yeah, we have stations that are more riverine and estuarine that have some of that freshwater influence. At those, if those were a part of the assimilation process, we have higher skill there. Even the ones that there's validation between, we still have some skill, but the more riverine and freshwater information we can get, the better off the model will be, especially if we can couple them. So I don't know if I answered that the way that you hoped.
I could add one small part to that, is that yeah, we are in the evaluation and testing of Cora, we've been looking at those stations in particular. We've just started some research on trying to figure out, right, why certain errors we see at certain times a year. Is it precipitation based? Is it, some kind of larger surge? What's the, component or contribution of the tides to the errors, et cetera? So we are starting to dig into all of those parts. Precipitation and freshwater, yeah, discharge and inflow is one of those factors we're looking at.
Thank you so much for answering that. I will briefly step away from the questions real quick, and just so I forgot earlier to mention that our next webinar in May, one of our partners at USDA Southeast Climate Hub will be talking about their hurricane preparation and recovery commodity guides for producers in the Southeast. I think that will be very valuable. So stay tuned for our next webinar next month. And then I'll jump back to questions here. So I'll just read out the question here, and we can work through it. It's for John and for Anna. Person said that apologize in advance that if you covered this in your presentation, they missed some of the presentation. But they were asking about comments on reliability of the slosh models and how it compares. It seems that emergency management usually relies on slosh for surge, etc.
I can't replace any kind of model like the slosh model. That's a forward-looking model, I do believe, and that makes predictions from it. So everything that we're doing is reanalysis. It's retrospective. So I'm not sure. Actually, I'd love to learn more about the slosh model, but I think just as a whole, we've learned from people and our academic partners that they're interested in using Cora as a foundation for improving their storm surge modeling, just because of the richness of information. John, did you have any other ideas?
There is some decent literature out there looking at surge-based models to slosh for accuracy, right? And slosh was developed, as you know, for running a variety of parameters, particularly for hurricanes and tropical systems, right, in a very quick fashion. AdCirc does take a lot more care. It takes a lot longer to run. However, exactly what Anna said, right? We're using this right now as part of a retrospective, kind of a hindcast reanalysis point of view that we're looking at. Whether we run the Cora model in a forecast point of view, that's something that we'll look into in the future.
Awesome. Thank you guys so much for answering those questions. I do not have any more in the chat, so we'll go ahead and conclude since we're at the top of the hour. Again, thank you all so much for participating and tuning in, and also thank you again to our presenters who provided so much great information today. If you have any questions, feel free to reach out to me, and I can direct your questions appropriately. My email is elliot.wickham@noaa.gov. Thank you all so much. I hope you all have a great rest of your day and week. Thank you.
Thanks, everyone. Thank you, Elliot, Pam, Shelby. Bye.